Now, still using the step up, step down approach, similar analogous to what we did earlier, quite a bit earlier, for the simple harmonic oscillator, the SHO. There's a limit to how far you can step up or step down. You can't keep applying the step up operator or step down operator too many times, because eventually you run out of possibilities, and the constraint operating on you is, from earlier theory, remember m squared has to be less, well, let's equal to L squared. I mean, well, you can't, your m cannot get too large, right? There's a limit. It can't go beyond L squared. So let's assume that there's an eigenvector, call it t, psi t, t for top, yes, the top one, the top non-zero eigenfunction. And if you step up beyond that, you get nothing, right? Because it's the top one. There is no higher one. It's the top one. So psi t for top, right? St, such that if you apply the step up or the raising operator to it, you get nothing, right? And a similar logic, this is m squared, so there is a minimum m. We found that before it was minus L, so you can't, because of the square of it, so a minus negative m is also constrained. It cannot go down too far. Okay, so let there be an eigenfunction b for bottom, which is the lowest, the least in a sense. And so if you try to step down that one, you get 0. You can't go any lower. There's no lower eigenfunction, because psi b for bottom, is the lowest one, the bottom one. Okay? So similar logic. So the lowering operator, the step down operator, psi b, will be 0. Okay. Now, given the relations from the previous session, still quite a bit of algebra in this one as well, and homework. We're getting, we're now about 3/4. Let me just check. So, 2/3. Okay, we're 2/3 the way through the course. So, and it's a senior level course. So we expect things to get a bit harder. So, knowing these two relations now, and the previous relations we had, we can now actually calculate the spectrum, all possible values of the eigenvalues, right, for lambda and mu, using this stuff, right? So now, using the relation or the equation x circle, you can't see it, but where is it? Oh, it's complicated. Even I read it, that wouldn't mean anything. All right. So go back to the previous session. Have a look at the equation x circle. Now, using that, multiply that relation, that equation, on the right-hand side, both sides, by psi t. So this equals this, and because psi t is the top one, if you raise it, if you step up, you try to step it up, this will give you 0. So all this is 0. Okay, all this is 0. Now L squared psi is lambda, just an eigenequation. So this is just lambda t, and here you've got the square of the z component. So that'll be mu t. Now, why is it not lambda t? Why not? question. I'm going to have to think about that. So you can think about that as well. Why is it not lambda t? Why does it seem to be true for all? What is lambda? Lambda is the eigenvalue of the allowed angular momentum. All right. Okay. So that doesn't change. Okay. And here you'll get a minus h bar mu, well mu t, right? And all that's 0, and therefore this inside is all 0, so therefore lambda equals all this. So lambda is mu t outside, mu t minus here, okay, plus h bar, right? So I've got an expression now between lambda and the highest component of angular momentum. This mu here is sort of like an m. Right? Now the m's can change for a given lambda. I guess we'll end up showing that this ranges between plus and minus lambda. This will be like the L in time, but we're not quite there yet. Right? Now a similar logic as for these two lines, but using the lowering operator, the step down operator, right? And so do something similar to here. Instead of having plus here, you'll have a minus, and this will change a little bit. And, well, go through the algebra, and you'll end up getting something similar to this, but instead of t here, you'll have b for the bottom component along the z-axis. So you have mu b into mu b minus h bar, right? But they're both the same lambda, and therefore this equals that. Alright, now if this equals that, then mu t is equal to minus mu b. And you see we're getting there, ranging from L to minus L. It's getting there. Right? Now, the steps between these are multiples, they're in units of h bar. Where'd that come from? That's from the previous session. Right? The step operator takes it up, takes the mu eigenvalue up by h bar, or takes it down by h bar. So it's stepping up or down in units, in increments of h bar. Right? So that means the difference between